Hi everyone, welcome to 142nd Stanford MedAI Group Exchange session. This week we have Onkar with us talking about his work on using diffusion models for medical imaging applications. Onkar is an AI researcher who previously worked as a research scientist at Yellow.ai, leading innovative projects and academic collaborations. Soon he will begin his PhD at UIUC. Onkar's expertise span continual learning, generative modeling, NLP, and computer vision with a strong focus on multimodal interaction. Onkar, thank you very much for joining us today. Before we start, do you have any preference on how you would like to take questions? Do you have designated breaks in your talk, or can we interrupt you in the middle?
Yeah, interruption in middle it will be fine actually. It should be. I feel interactive way would be nice. Like,
Okay, so in that
yeah,
case, everyone, let's try to make this session as interactive as possible. And without further ado, let me hand it over to Onkar.
yeah. Hello all. So today I will be presenting this session, and let me share my screen. And please interact and please raise any doubt or queries if you have during the presentation. So yeah, myself Onkar Susladkar, and event like unfortunately my colleague Gayatri Deshmukh, she is not available for this video lecture. So on behalf of her, I will be presenting. So yeah, so today's topic is like different model in medical imaging. So this is our paper, MedDelina, like scalable and efficient medical image segmentation by controllable diffusion transformer. So this has been accepted at MIDL 2025, and we will be presenting this in coming June actually, coming July. So yeah, so current problems in the medical, basically medical image segmentation. So we all know like there is a poor generalizable, poor generalizations to the unseen data sets. Like it's little bit still it is little bit difficult. Like even the any medical any medical image segmentation model trained on even the larger data set scale or large scale data set, but still it's can't able to generalize on the unseen data set or the unseen class itself. Limited another challenge is like limited data label data availability. Like it's still like very difficult to get like 3D data, like well labeled 3D data. High variations in the image modalities like CT, MRI, RCT, or this basically into inside. If we talk about the MRI itself, like there are T2 MRI, T1 MRI. So getting each samples for each modalities is little bit difficult. And one of the major task in this medical image segmentation, that is the boundary delineation. So basically like across the even across for the scene classes, like it's like very difficult to get a perfect boundary generalizability across like different organs. Like even if we talk about the liver or the stomach, so if we try to segment the abdominal organs, like it's a little bit difficult for the even for the large organs and the small organs also, pancreas, just like pancreas or spleen. So it's a little bit difficult to boundary delineation. So we called it, the paper name itself, like MedDelina, so medical image and with the delineation, boundary delineation. Yeah, so like there are a lot of different existing methods like self pre-training, fast adaptation, but overfits. Like there are transunate, swininator plus plus. Like there are a lot of previous generalizable methods. Like, or there is a now recent methods like SAM2, SAM2, which can be also very good method for 2D image segmentation basically. And generic pre-training is task like better for the a lot of things are there, but lot of models struggles with the balance generalizations and efficiency actually. Like those models are like much bigger and which can able to capture better features, and which can better generalization, but it's very difficult to train across. And so resources and resource, they are very resource heavy actually, and it's not so efficient. So we call, that's how our method model come into the picture. Like our model is basically like generalizable, it's efficient, modular across is like we can modular it through any diffusion, any diffusion type model, like whether it is a stable diffusion or whether it's a VQ diffusion, anything. Like we can scale it across anything, and it is scalable actually. Like you can go from 200 million to 300 million, 300 to 400 million very easily because of the it's a 100% transformer network. So yeah, let me go through this model, and if you have any doubt with the how the model works, please interrupt. So yeah, so this is our mask. I am basically in a segmentation mask. We encode with the pre-trained VAE encoder, like to get the ZM, basically Z mask latents actually, and on top of ZM we diffuse it to get the ZMT, like probability of ZMT given ZM. We diffuse it, basically the forward diffusion. We apply the forward diffusion on this. We do the patchification, basically our when we encode from the VAE, basically we have the 4-dimensional shape. We have to convert the 4-dimensional shape to 3-dimensional shape in format of batch, comma some sequence of tokens, comma some embedding size, to pass it through this transformer network. This is NDIT blocks. Simultaneously, what we do, we take the IO, basically the original city image. Basically, we take the 2D replica, basically 2D replica of that particular city image, and we pass it through the another VA, same freeze VA encoder. Basically, these are the weight shared, and we get some latent representation followed by the zero con. And what we do, basically, we concatenate basically the original representations and the mask representations, and we do some same patchification, and we pass it through this controllable transform block. So this, from every full network, only this part is only the trainable, and the one last layer of the decoder, we pass it through this controllable transform block, and that's how we give the conditional attention to the our mainstream transform block. So if you can see, like, from the each transfer block, after every scale part, we are giving the, basically we are adding the features from the into the mainstream block. So this we repeat, basically if we have the n transfer block, so we don't have to use the n control block, so we can only use the, out of n we can only use the k controllable blocks, and in our case we use the k as like only 4 blocks, actually 4 to 6 blocks. And if you talk about the NDIT block, so n is nearly equal to 24, so we don't have to give to the like full forward pass to the till up to 24 DIT blocks. And followed by, we just do the repatchification, and after repatchification, here we apply a new formulation of one diffusion model. So here we are doing the basically zero shot sampling to get that latent representation into the basically to get that pure latent representation into the image form, basically in this image form, and we decode it to get the mask actually. And during decoding, like we take the two losses. One loss is basically the segmentation loss, basically the cross entropy followed by the dice loss, and another loss we take at the diffusion loss. And both the losses, this is segmentation loss and the diffusion loss, we add these two losses and we penalize whole the network, actually like entire network has been penalized with the same optimizer. So that's how our this MedDelina, basically like this whole architecture is about. And yeah, moving on to the next slide, like we will see some how we trained it, actually like what are the things we use for this pre-train, basically the training this network. So the data sets we use for this training is like Atlas 8K data set, which contain 8,000 3D CT volumes, and we slice it across the 2D scans, actually to get a better representation. And because our network works on the 2D space, so we slice it along the 2D scan, so nearly equal to 1.3 million 2D scans. And we use the self supervised pre-training. And the objective was like main objective for this pre-training was basically this DIT model. Basically like this DIT model is trained on natural images, actually uh, natural scene images. It haven't seen any sort of medical images. So to get the better adaptability for the medical images, we train this network for on Atlas 8K dataset to get the medical image features alignment between the networks and all. After that, for the downstream task, basically again we use the same downstream task, that is the BTCV. BTCV dataset, multi-organ CT dataset. Then there is AMOS dataset, which contain CT as well as MRI, that two multi-organ. And these are the two our internal datasets. That is SEER MRI 600, that is the cirrhotic liver MRI dataset, and the third is the pancreas dataset, which and these all basically these two dataset are contain basically MRI 3D images. And we supported models in the 3 stage, like fine tuning, basically full training on the target dataset, either like BTCV, AMOS, or SEER MRI 600 plus, or we are doing the few shot training also, like we analyze our network on, let's say, if we use only 1% data, or if we use only 10% of data, or we use the 25% of the label data, then how it works. Or we also check like the how the direct inference happens in the zero shot manners, like if we just do not fine tune, if we don't pre-train just with the pre-trained network, we just do the direct inference on the on these any of the data set, then how it works. So if we see that, like even with the fine-tuned manner, our MedDelina, basically like MedDelina outperforms all the previous diffusion baseline, that is diffusion transformer, VQ diffusion, MedSegDef, which is again one of the good baseline for the medical diffusion in medical image segmentation. Then there is control net, very, very famous control net actually. So our method is like outperform all the previous baselines. Even in the zero shot manner itself, if we can see like our method can able to surpass all the previous baselines. And this training, like not to like to get the proper ample to ample comparisons, we train all the networks like control net, medsec def, vq diffusion, dit on the same in our same setting actually. So there is no gap between, basically there is no training gap, so it's like 100% ample to ample comparison. We also seen the qualitative, basically qualitative benchmark on the few shot, basically on the few shot setting. That is like if we use the only 1% of the training data on BTCV and AMOS. What if we use the 10% training data, and what if we use the 25% of the training data? Even with all the settings, even in the few shot setting, our method can outperform previous baseline. In the paper, like in the slides, I haven't mentioned the baselines like NN unit or NN trans, basically NN synergy net or synergy net, because like uh, really the presentation is more focused towards the diffusion based image segmentation method, so that's why I couldn't mention it in the slides. But in our paper, like we have also compared along with the NN unit, NN formers, and all those previous baselines, which are more focused towards the medical, specifically for the medical segmentation.
Onkar,
Hi.
oh, sorry.
Yeah, sorry. Yes, yes.
Yeah.
Amara, you go ahead. Yes.
Okay, thank
Yeah,
you. So I had one question, and I think we have one
yeah.
question from the audience as well. My
Okay.
question was when you started the introduction, you were talking about the delineation of boundaries between different organs, so we can see the overall performance is better.
Yeah.
But do you have like some intuition of like, is it actually doing delineation better, or is it? I mean, is there anything to say that yes, it's better because it can delineate boundaries between different organs better? And I think
Yes.
audience question is also kind of on the similar lines. What is the intuition why your method is better than the other methods?
Yeah. So one of the major reason is like basically intuition is basically our with our method, like we can able to separate the boundaries between the two organs very clearly actually. So for with the qualitative results, we are going to show that like how it is like, it is like much easier to separate the boundaries because of the diffusion task actually, and better generalizable capability of the diffusion models basically. That is the main reason, like that's why like it's perform basically the model's performance is better than other baselines actually. So let me go with the these things. So if we see that like yeah if we see that like basically like the boundary conditions, like we can able to see like our method like can able to separate the boundaries very clearly actually than the control net or the specific dit actually. So main reason, so what we observe, like the main reasons to get the better result is basically delineation itself, like the boundary condition itself. That's what we observe in the most of the part, basically overlapping organs, or in the, this is the main reason for this to getting the better results. What we observe. We also inside the paper actually we have also plot the tsne plots actually with the different organs actually, and for the different basically for the different methods as well. And from the tsne plots itself we can clearly mention like we get the feature wise better feature wise representations for each of the different aspects of the organ more clearly than the different baselines actually, like the control net or dit. So that is also one of the reasons like we are better actually in terms of uh,
And
in the comparison.
Thank you. I think we have like two follow-up questions.
Yeah, yeah.
My follow-up question is that has it something to do with the organ size as well? Like, do you see in your qualitative assessment, do you see that your model is better because it can do better for the smaller organ
Yeah,
size?
smaller. Yeah, yes. So for the basically for the smaller organs like pancreas or the spine, actually, our model can able to do better segmentation actually. So that is also what we observe actually. Not only for the bigger organs. So of course, in the bigger organs, like the segmentation part is easy also. Like, and sometimes like more traditional CNN based approaches also, like we can able to capture the boundaries very nicely. But in case of smaller organs, like even like adrenaline gland, or
Mhm.
if we talk about spine or pancreas, basically like most difficult ones what we observe is pancreas. So in that case also we have seen like we are getting like proper boundary condition and the aging condition actually. And in our code actually, like in our GitHub actually, we have also released the 3D. Uh, Basically, we did this inference on the 3D itself, like, and we have basically 3D mesh structures of each of the segmentations. We have also released that so that you can also view in the NII viewer also. So we can
Okay.
able to clearly in that also we can able to clearly see that like how the pancreas has been segmented very neatly with respect to the ground truth or with respect to original image. So
Okay.
yeah,
And I think follow-up question from the audience is that can you
yeah.
explain more about the self pre-training and the generic pre-training? How are they different from your method?
Yeah. So let me explain. So generic pre-training for these different, basically for these diffusion models are follows. So in the generic way, what we do actually, like these diffusion models are basically for the like text to image generation models basically. So in generic pre-training, what we do basically, we use the some text part, like let's say if we talk about the natural image generation. So what we do, like let's say we wrote a give me the image of cat actually. So basically conditions are basically based on the text actually, and we train these diffusion models based on the given the image and the given the text captions actually. And we train on like millions and billions of the images, and this is basically the generic pre-training of these diffusion models. And in our case, basically we are specifically targeting to generate this particular mask, basically this particular segmentation mask from this image actually. And one of the major thing of what we are using is basically this zero shot sampling actually. People are only using in the generic pre-training, people are only using the diffusion loss and they penalize all the network. But here we apply some Twiddy's formula actually, that is the zero shot sampling. To get the to basically to get the learned representation, we pass it from the decoder, and the decoder will now map to the basically number of classes in the for that particular segmentation map. So it's like it's 100% for the this training is meant for the medical images rather than natural scene images actually. Yeah,
So just following up on that, so if you're
yeah,
drawing a comparison or analogy with text conditioned diffusion models,
yeah.
is it okay to assume that in your case, the condition is coming from the original image
Original, yeah, exactly, original
as
image, as well as we are also and we are also we are not only using the diffusion loss, we are using the segmentation loss as well, like at the end of the decoder we are also getting the full mask at the decoder end, so that we will get the proper boundaries and the proper everything actually. Like we are learning this decoder as well. In generic pre-training, we don't learn this decoder, we only learn this denoiser network actually.
okay, but in your case, the
Yeah,
output is there is no output of like the denoised image. The imaging output, the 2D space output is coming from the mask itself.
yeah. Basically, during inference, we don't
Mhm.
use the mask itself. Basically, we will only give the pure noise,
Mhm.
and we iteratively decode that noise till we get the pure noise. That pure noise, we will just decode from the decoder to get the mask actually, to get the by basically multi label mask,
And
and
while it is
with the
being
condition, yeah,
condition
and the
of the
condition
original
from
image.
the original image. Yeah,
Okay, thank you.
yeah. Any other doubts, please?
I don't see any more questions from the audience, so maybe we can keep going.
Yeah. I think it will be better like the audience directly interact like instead of like writing will be little bit difficult sometimes. Yeah.
Yeah, so anyone, if you have any questions, just please raise your hand and we can call on you.
Yeah.
I think somebody is also writing another. After pre-training, which part is used for transfer?
Yeah.
Dr. Liang,
Yeah.
do you want
So
to expand upon that? Or Onkar, did you get the question? After pre-training, which part is used for transfer?
transfer learning, right?
I assume
So
so.
Or
after you have to transfer somewhere. That's right.
sorry.
You are pre-training. That's right.
Yeah. We are pre-training this network. Yeah.
In order to use your network, you have to do transfer somewhere because you use mask during the training phase.
Yeah. We are using the mask in the training phase.
Mask.
Yeah.
I know. So which part of network you use for transfer?
Transfer as in
How you use your network after pre-training?
Oh,
Yes,
okay.
inference,
Yeah.
how would it be used at
Okay. Yeah.
inference time?
Yeah. So I forgot to add the inference diagram. Yeah. So after pre-training, what we do actually, like we only take the pure noise, like pure random Gaussian noise, with at ZMT basically. So ZMT will be the pure Gaussian noise. What we do, we
You
pass
cannot
this
use
noise.
mask anymore because you
No.
apply.
During inference we don't use the mask actually. Yeah.
So what do you give input? But you still have input.
Yeah. We only give basically. Yeah. So we only use this part of the basically pre-trained DIT module and this part controllable DIT module. That's it.
That's my question. Okay.
Yeah. Okay. Yeah. So we only sorry. Yeah. So we only use the pre-trained DIT module and the controllable DIT module. That's it. Nothing else. We don't use this part. VA encoder basically we don't use it.
I still have some difficulty to understand why your method is better. Intuitive. What you did make you better than other methods. You said you can do small object better. Why your model can do small object better?
Yeah. So one of the main thing why we can do the small object better is that uh, we are not only penalizing the loss, basically the diffusion loss. That is the basically we are not only using the uh, we are not only predicting the noise, but the after predicting the noise we are also getting the some latent representation. If you see that like zm0 to decode this latent representation, and after decoding this latent representation we are calculating the segmentation loss as well at the decoder end. And the segmentation loss itself is nothing but the basically the cross entropy loss followed by the uh, dice loss actually. With these two losses, if we penalize with these two losses this whole diffusion model, like basically the whole denoiser network, then what we observe is that like we it can able to generalize better across the boundaries actually, because the mean is getting shift. Basically the variance will be stayed at a same level, and we are just shifting the mean actually if we take the segmentation loss. And the segmentation loss is basically the supervised loss, direct supervised loss. So the
Okay.
mean will shift at the basically the mean will only shift and the variance will stay at the same point.
Okay, thank you.
That is the main. Yeah. Any other doubt, please?
No, I think we can. Oh, G, you have a question?
Yeah, I have a quick question about the patch 5 in the beginning. Yeah, so
Yeah.
does this model fit the 3D images or
Yeah, basically but at that time actually we don't have the 3D VAE trained actually, but this same network with no excess change or anything, we can able to fit for the 3D as well. Same
Okay.
network can be easily fit for the 3D as well. But just the condition is like we should have the VAE basically. These VAEs are there, right? That should be trained for the 3D.
Okay, then Patchify is also the making small boxes from the
Yeah. Basically voxels to the token levels actually, token level sequence.
I see. And okay, is it in by any chance is it or from the 40 dimension? Is it 40 dimension from the beginning, like in the 3D?
Yeah, basically b comma some number of channels comma height comma w. Yeah, 4D channel. basically 4D image.
Yeah,
If we include the batch, then it is 4D. If we don't include the batch, then it is like normal RGB image, like 3D shape.
okay, yeah, thank you.
Any other doubt?
No, I think we can
Yeah.
move on.
Yeah. So yeah, so these are some qualitative results in which we can able to see like we have seen the different ROIs basically. We can see that like our method can able to basically generalize, and which it can make the delineation between the boundaries actually. Like if you see, you can clearly see it. And in the paper actually we have mentioned more better examples actually, and more better analysis towards this part actually for this quantitative result. And again, like another main thing for this paper, basically for this model is, if you see that like with the our model, like which has the comparable inference latency as per the DIT basically, but with the same, just little bit increase in the parameter actually. And we can able to inference like do the 512 cross 512 inference in just like 2.88 second actually. So uh, which is more efficient for any diffusion model actually, rather than if you go with the MedSegDef, which was the SOTA, previous SOTA, which takes nearly 8.89 seconds on V100 actually. And diffusion, which we could diffusion take 3.11 second, and our method can take like 2.88 seconds actually, in terms of inference time and model complexity. So this is like what we saw, the best trade-off between the speed, size, and accuracy, and which can also be reliable, can be deployable, easily deployable for the clinical and real-time use cases as well. Yeah. And this is how that's it for the like MedDelina actually paper for the diffusion model for the medical image segmentation. Now this is a second project what we which is currently under review at the ICCV. This is the ViCTr actually, like vital consistency transfer for pathology aware image synthesis actually. So yeah, so in this paper, like these are our key contributions. So we develop a two-stage framework, that is ViCTr. We develop a two-stage framework which has the broad compatibility, efficient sampling, better segmentation results, high image fidelity. Like we have scaled this network for even for like bigger resolutions like 1024 cross 1024 or 2048 cross 2048 as well. And abdominal MRI, we are the first one at that time, like who are generating the 3D abdominal MRI, basically abdominal MRI from the segmentation map actually. So let's go with the step by step. Firstly, let's go with the statistical comparison between the different methodologies. If you see like reflow, flow straight fast, distribution matching distillation, and ViCTr, basically these are the different algorithms. And our algorithm, basically ViCTr algorithm, which can match to the exact ground truth distribution actually. This is a blue is the ground truth distribution, and this brown is basically the distribution produced by the ViCTr actually. And we are comparable with this ground truth distribution actually. So yeah, so this is basically like the ViCTr architecture. Yeah, so this is the ViCTr architecture. uh, this is mostly for the generating the CT/MRI images actually. So again, like here also we use the Atlas 8K dataset, and instead of diffusion, like traditional diffusion, we have gone with the flow matching actually. Like the algorithm here we use to denoise the image, noise and denoise the image, that is the flow matching, that is on the straight path, fast and robust for the generating the high quality images. So what we do actually here again, in the pre-training stage, we take the text encoder. Basically the text prompt is nothing but the text prompt we have derived from the segmentation map itself. Like we have given the organ names actually, like
I think we lost our speaker for a while. Onkar, I think we lost you for a while.
Oh, okay. Sorry.
Yeah,
Yeah. Am
that's
I
okay.
audible now?
Yes.
So where did you lose actually? Sorry, actually.
One slide ahead. You can go ahead. Or you were showing
Okay,
the
this.
architecture. No, you were showing the architecture.
Okay.
Yes, this
Sorry.
one.
Okay. Fine.
Yes.
Yeah. So so let me go again. So this is our vector architecture actually. So so in for the we have used the two stages. Stage one is the pre-training actually. So pre-training, why we use the pre-training again is for the same reason, that basically this 5e basically this 5e is basically trained on the natural images, that is the natural images prompt and the mostly on the natural images side. So to get the better generalizability and adaptability for the medical images, we use this 5e actually. We train this 5e, and to train this 5e, we haven't used the normal diffusion training. Instead of using the normal diffusion, we use the flow matching actually here. So which is fast and robust actually, like across the training the diffusion models. Flow matching is currently it's a state of the art the training phase actually. So what we do actually, like we take the prompt actually, x prompt, xp is the x prompt. So x prompt is nothing but the text, basically the organ names actually, which contains in the CT image or the MRI image actually. So what we do basically, we encode the text prompt, that is the basically the organ names from the text encoder. What we do here, like we take the segmentation map XS and the original CT image, that is XI. We pass it through the VAE encoder to get the ZS and the Z.
We have lost our speaker once.
Yeah, looks like it. Everyone, let's just wait a couple of minutes for the speaker to be able to join again.
Now I think is it fine now? Actually, my internet got
Yes,
little bit on.
that's okay. You were again back on your architecture slide,
I will just
explaining the BA encoder.
So basically, like this net now is fine, right? Now it is, there is nothing.
Yes. Right now we can hear you.
Okay. So let me explain it again. Like basically in this network we are having the like three main things. Like one is the text encoder, that is the we are to get the to encode the prompt. Second is the VAE encoder, again to encode the segmentation map, and the third is basically the city image, VAE encoder for the city image actually, to encode the city image. So all these representation basically the segmentation map representation and the city image representations we concatenate, we pass it through this partially training denoiser actually. So in this case you can use any architectures, like you can use the flux, you can use the stable diffusion 3, or you can use the we make this architecture or the we make this training strategy in such a way that you can use the any sort of the diffusion models, like pre-trained diffusion models on the natural images. Like you can use the stable diffusion XL or any sort of model. So if you just want these three things actually, and it should be partially trained. So pre-training, we are just doing the partially train, and partially train as in, like, instead of training the full layers inside the this denoiser, like end-to-end training, we are using only the few layers training. And how we are going to recognize what to train and what not to train, basically we are using the elastic weight consolidation. So we are firstly analyzing the gradients, like for what particular layer there is a high gradient update. So we are only training those layers, and which don't have the and which have very low gradient updates. We are just keeping it as a freeze actually. So that's how we are training this. That's how we have concluded basically the stage 1 training actually, that is the pre-training. And again, another novelty for the this training is we have introduced the new formulation for the 2D's formula in the flow matching actually. So previously there is no formulation previously to get the one shot sampling in the flow matching. So but now we have done like one little bit hack actually, and we solve one OD actually to get the 2D's formula for the one shot sampling actually for the flow matching. So that is the one more novelty in this paper actually. Coming on to the stage 2, that is the for the fine tuning actually. Like what if like we pre-train our network, and we want the basically yeah we want to generate images with some different kinds actually. Like we want images of the we want like CT images instead of CT, like we want the MRI images. So basically we have pre-trained this on the Atlas 8K, that is the CT images, but we want to fine tune it on the particularly for the MRI images, like AMOS MRI set or any MRI set actually. So this is our stage 2 fine tuning network actually. And what we keep here, the most of the things are freeze actually. We are only training this LoRa adapter part actually. So we are only training the adapter part for this particular network to get the pretty predicted CT and the CT or MRI image actually for this with the fine tune approach. If you see, like there is a like segmentation mask XS, then there is a CT image. There basically XT is the CT image. We are doing the same thing actually. Like basically we are getting the representation on the CT image. We are applying the basically we are noising the CT image. We are concatenate both the CT image and the segmentation map, and we are passing it from the basically the two neural network, that is base network and the adapt network actually. So and again we take the consistency loss, we take the diffusion loss across all the we take the diffusion loss across the both the network. Then we take the global loss as well. Like if you see this, we take the global loss. So there are like 6 losses to penalize this LoRa adapters actually, and that's why like we get a like for the we can get because we are penalizing the total number of 6 losses actually altogether. So we have seen like these are the qualitative results across the different data sets, that is BTCV, AMOS, and cirrhosis MRI. And these metrics are basically nothing but the FID metrics actually. If we use the normal fine tune, basically we don't follow the vector based fine tuning method, then basically our FID is pretty high actually for the even for the stable diffusion XL, stable diffusion 3 PixArt or Flux actually. Like it's pretty higher side. But if we use the vector based trading strategy, our FID is like our FID is more better actually than other baselines. And one of the major thing for the use the vector is we all know that like the generating the high quality or the synthetic images generally requires much higher diffusion steps, like that is 50, 30, or at least 25. But in our case, like we only want like 5 to 4 diffusion steps or even 3 diffusion steps, like to get the very high and very good high resolution image synthesis actually. And inference time is also very low actually in our case. These are some qualitative results for the generation actually. Like so this is the BTCV generation. So for this particular mask, basically these are the two masks. We are our basically like Flux with the vector fine tuning. Like we can able to get a very proper very proper basically CT image actually, and which can also be generalized on the AMOS data set, that is on the MRI side of it. So for this particular for this particular mask, we are able to get a very proper and very bright image actually for the MRI image actually. So that's sort about the qualitative result. And we also did the pathology generation actually. Like what we did actually, like we have also fine-tuned our method, basically the ViCTr method, for getting the generated serotic basically generated serotic images actually, serotic liver. So if you see that this is the non-serotic liver from the lids actually, and we are able to generate the serotic patterns actually on the liver actually. So mild, and we can control these basically, like we can control this generation nodularity between the generation with the text prompt actually, by giving the condition as the mild, moderate, or the severe actually. So we can just write the generator serotic liver with the T2 MRI with the mild actually. So it can literally generate the uh, for this particular CT, it can convert CT into MRI first internally itself, and that too it can generate the image up to like severity level up to mild, moderate, or the severe actually.
Onkar, this
Basically this,
mild, moderate,
yeah,
and severe, are these like clinical, like
yeah, yeah,
clinically
yeah, yeah.
marked categories for
Yes, yes,
cirrhosis?
yes. So this is our internal dataset, which we have open source, which we have open source in the last paper, our uh, cirrhosis CIR 600 plus actually. And in that we have moderate, we have marked actually, like which is the serotic, which is having the severe case, which is having the moderate case, and which is having the mild case actually. This we have labeled actually, and we
Okay,
have
just
in both.
and yeah, and
Yeah,
just
yeah,
so I understand the utility completely, um, if you're providing the mask of, let's say, the liver and
yeah,
not the other organs in the same
yeah,
slice,
yeah, yeah,
uh, you would still be able to generate like a realistic looking
yeah, yeah,
mask, or you're
realistic.
or you're trying to, or the goal is to be able to fill that mask with a realistic looking organ. Is it the goal is to
Yeah, yeah,
generate
yeah,
the full
exactly,
slice or
exactly.
just the
Yeah, basically the goal is to generate the fill that particular mask actually.
fill the
If you
particular
see
mask?
like
Okay.
yeah, yeah, but in this case actually we are filling that particular mask with the serotic properties actually.
Mhm.
Yeah, whether it is the
Uh,
mild, severe, or the moderate actually,
and this property is controlled
with
based
the
on
text actually,
text.
text.
So basically,
Yeah,
you can
text
say
control.
severe, moderate, or mild, as well as like none,
Yeah,
like generate the healthy liver.
yeah, healthy liver as well. Yeah, yeah.
Okay.
If we give in the text as a none, then
Mhm.
it will only generate the healthy liver, or it can generate the liver in the MRI fashion actually, how the MRI will look actually.
Okay. Thank
So,
you.
from the we have also seen in the paper, we have also shown the transition results, like from the CT to MRI, particularly for the T1 and T2 separately actually. So these also results we have shown actually, like the transitive property of the model actually.
And just out of curiosity, like this transitive
Yeah,
is kind of two-way, or you just go from like CT to MR?
both two-way actually, two-way, from the
Two-way.
MRI to CT as well, CT to MRI as well,
MR as
from
well.
T1 T2 to T2 to T1 as well. So all the
Okay.
cases.
Okay.
But this is
Thank you.
only we have done it for the 2D level.
Mhm.
The next paper, that is ViCTr plus plus, we are going to in the 3D space actually. Like we
Okay.
are able to generating the full 3D
Mhm.
full 3D image actually.
Okay. That's very interesting. Thank you.
Yeah, and
Would you go back to
yeah,
the
yes,
the
yes, yes,
architecture slide, please?
yeah, yeah. Sorry, yes.
Yeah, I think
Stage 1 or stage 2?
yeah, stage 2. So for
Yeah, okay.
the beginning of the in the prompt, so would you give me some example of what is the prompt on the first of the on the
Yeah, yeah, yeah. Yeah. So the prompt is nothing but the prompt is basically what image it need to generate, basically the generate CT image or generate the MRI image. In that, if we want to generate the MRI image, then we are explicitly giving the generate the T2 MRI image or T1 MRI image, and followed by the organ names actually, like what are the organs we want to generate, like stomach, stomach, liver, and all those things actually.
Okay, then does it, but this part is not related to the mild severe that we just discussed, that this part.
Yeah. So this is, yeah, exactly. So there are two different things we have we have shown in this paper. One is the complete basically from the segmentation map, where I try to generate the whole CT or CT/MRI image, and the second stage is basically we have shown the result for the pathology generation on top of any CT or MRI actually. How we can include the pathology on the particular MRI. Like in our case, like we have shown the cirrhosis actually, like liver cirrhosis.
Okay, I see. Yeah.
Yeah, basically we have shown the two types of qualitative results, basically three types. Uh, one is basically the from the semantic map, how we can generate the CT
I think we,
MRI image. Second is the how we can generate the, and the third is basically transitive nature actually. Transitive nature, yeah. Hello, am I audible?
yes, yes, you are.
Yeah. Okay. Okay. Any doubts in this part?
Oh, no,
I know this. Yeah.
yeah, thank you. Yeah.
Yeah, I didn't cover the mathematics of this because I wanted to make this basically this slide and presentation to be application based actually. So I didn't cover the mathematics of flow matching, how the flow matching goes into the Twedis formula. That is still in the paper actually. And if anybody interested properly into the mathematics and all, like they can mail me and they can separately meet and we can discuss regarding that particular maths as well. So that is also another part actually for that. But I didn't cover the mathematics in this slides actually, because I wanted to keep it as applicativeness as possible. Yeah. And these are some counterfactual generations. And after that, what we have seen that, like if we generate the synthetic data by our method, that is the ViCTr, we can able to get a better segmentation accuracy. Like let's say you have some you have some data set, some let's say 100 samples. Then we add the we generate we synthetically create the data set for more 100 samples we synthetically generate. And after that, we train the network. So in any segmentation network, you can train like NNUnet or NNformer or SwinUniter or anything. Then our with the quality of the generated synthetic data by our method, the segmentation model learns a better segmentation maps actually. So that's what we see. It learns better than doing the augmentations actually. That's what we observed actually. So this is the ground truth, and this is the default if we don't use anything like, not augmentation or not any synthetic data. If we use the augmentation, if we use the flux, and if we use the flux with the ViCTr algorithm actually, like with our algorithm, it can able to generalize better actually. This is for the left kidney and this is for the pancreas actually. So we can able to see like we can able to cover like proper area across all the sample actually, or proper organ actually. Yeah. So that's what these two papers are all about actually. So any doubts?
Thank you very much, Onkar.
Yeah.
Um, so before we move on to questions, I think we should give our speaker a virtual round of applause for this very interesting presentation.
Thank you.
And after that, the floor is open for questions.
Yeah.
Thanks for the great presentation. So one first question about the Atlas dataset. So that so you use the Atlas 8K, right?
Atlas 8K, yeah.
And that has 15 organs. Okay. Do you know if they have like contrast and non-contrast CT?
No, they only have the contrast CTs actually.
Only contrast CTs. Okay.
Yeah, contrast CTs.
And in because like things look so different on CT depending on the contrast. So and even during the contrast phase, so you
Yeah,
have
yeah.
like arterial.
Yeah. We have the arterial actually. So we normalize it actually.
Okay. So it'll work for if my CT is in like venous phase or
Yeah. It will work. It will work. Yeah.
And
Basically,
then
what we observed, like
yeah.
in the Atlas 8K, they haven't in their paper they haven't mentioned like whether the contrast is like RTL phase or vinyl phase actually.
Yeah.
But what we have observed, like 80% contrast are the same, that is the RTL phase itself. Some images we have seen some different phase actually, like 20%, you can say 10 to 20%. But
Yeah, because then the follow-up to that is, like the CT total segmented data set, like it's smaller. It's like 1,200, but it has 100 organs, right? So any um any reason, like is it like you need more
we want more samples actually, that's what for training these diffusion models actually. So why we use 8,000 is that this Atlas 8K is that like we have seen that like with the more number of samples we can able to we can able to get the more generalizability towards the pre-trained diffusion models actually for the medical tasks. Because these diffusion models are trained on the natural images, and we just want that information of natural images to transfer it in the medical domain actually.
Okay.
Yeah.
And for Atlas 8K does it have tumor segmentations?
No tumor.
Okay, so
Yeah, so that's what these main drawbacks of this still method is that for the organ segmentations or like high level nodularity generations, it can able to it can outperform much better models like even the segmentation models. But it can't able to still its tumor, in case of tumor segmentation, in case of Bragg dataset or something, it still a little bit fails across previous baselines.
Thank you.
Yeah. Any other questions, please? And
Onkar, one question.
Yeah.
I know that you want to move from like 2D image generation to um, 3D. So one, like, what are your thoughts on how much more computationally expensive this is
I
going to
think
be? The other question is that the cirrhosis is a good example, but then I'm assuming that there would be pathologies which are not just like three classes, right? For example, if you're talking about a tumor, do you see like what kind of additional information are we gonna need? Maybe the location, the characteristics of the tumor. Like, how do you see this
yeah
kind of
so
expanding?
for the first question, that is we are trying to move from the 2D to 3D space. So one of the major thing what we have required and what we are training it actually currently is that this VAE encoder and decoder actually, to get the proper representations for that particular 3D data, we should require a good VAE actually. So that is good VAE part to get the proper latents. And there is no such VAE. There are a lot of 3D VAs, but that are only for the natural images, like natural like videos and all those things. So what we have thought of, like, to get that particular knowledge of that natural images, that is natural videos and all, to compute into the 3D space actually, in the medical 3D space actually, in the voxel space. And that we are currently into the training, like the training a good VAE model. And if we get a good VAE model, then the entire, like, the next process is the same as the training of this model itself. But the major thing is to get a good 3D VAE actually. So this is
Okay.
a major thing. And to get the 3D VAE, it should be generalized across all the modalities. Like it should not be only generalized across the CT, but it should be generalized across the MRI, RCT, TT1 MRI, T2 MRI, so all those things. And to get that, to curate that data set itself, it took like nearly 6 to 7 months for us. And for the
And we're
second
talking
question,
about still like the same part of the anatomy,
and
right?
we are still talking about the same part of the anatomy. But if we want to generate a specific tumor, basically, like let's say specific tumor on the location and or the size actually, if we get these features, like even inside the text actually, or if we get a proper radiology report, I think we can able to do that actually, like
Okay.
very realistic tumor generation. Like if we get a proper, like the gender of that particular MRI, age and size, what we want in what specific size, where we want, which at which part we want, do we want in the malignant phase or vinyl phase. So all those things actually, if we get, I think we can able to generalize this tumor generation in more realistic way, and we can get more synthetic data actually for training these segmentation maps actually.
Thank you very much.
Yeah.
Do we have any more questions?
One quick
Yeah,
question. I saw,
please.
like one of the speakers here, like a few weeks ago, was talking about Merlin, which is like a 3D CT VLM.
Yes.
And
Yeah,
one
yeah,
of the applications of Merlin is also like segmentation of organs. If there's any, so now you have, like, as a practitioner, it's like there's so many things to choose from. Like, should I use Merlin for my segmentation? Should I use your approach? Any like pros and cons with Merlin?
Yeah, so Merlin is basically the VLM which basically it,
But
as far as I know, like it auto-regressively decodes the map actually, like the segmentation map
okay,
from the CT image actually. And my approach is basically like instead of auto-regression, I believe into the like diffusion makes more sense actually.
okay.
But
That's
currently,
a
so
good
my
point.
method, yeah. So currently, my method works into the like if you go with the MedDelina and all, it works into the basically a 2D space actually. Although we are
Okay.
doing the inference 3D, but still like the internal computations happens in the 2D space. I believe like if we get a proper, that's what I said, like if we get a proper 3D model like 3D VAE, I think with the power of the diffusion or the power of flow matching, we can get more generalized and more better results actually across
Yeah.
these streams actually.
Thank you.
Like it can be comparable across I believe like the traditional segmentation methods as well for 3D, basically in the 3D space. Currently though it's not, if you see the results, uh, if you see like if we use the even if we use the uniter plus plus in the 3D domain, it can m dice can be achievable easily, it can be achievable up to 89 actually.
Okay.
But
Got it.
yeah, still it is little bit far actually.
Thank you. That's great.
Yeah.
Yeah. Are there any more questions? Okay. If not, thank you, Onkar, for the really nice and awesome talk. And I would ask our audience to give one more round of applause for this really
Thank you.
interesting talk and this awesome work. And with that, we are going to end our MedAI session. And this the video will be uploaded on YouTube, and the link will be shared. And if you have any questions that you want to ask Onkar, you can just reach out to him, and or we can connect you with him. Yeah, with that,
Yeah.
I'm going to stop.
I just wanted to give one thing, like
Yeah,
all
go ahead.
these both of these data set are our lab data set, like the Cirrhosis 600 plus, which are having the 600 MRI, basically MRI images, cirrhotic liver MRI images, T1 and T2. And there is another data that is PanSegData. This is also from the machine and hybrid intelligence lab, and this also both the data sets are open source, and you can use and you can cite our work for these papers actually. Yeah, this is a good contributions from our lab actually, like what we did actually, like open sourcing these two data sets. So if you include like nearly 1200 3D MRI images has been open source, so it can be good for the community. Yeah.
Okay, great. Yeah.
Yeah.
All right. With that, we are going to end the session.